What's up, everyone? Welcome back to OpenGL. Just a heads up for this episode, I am not going to be I will not be running the program at all, just because I'm still getting no output for some reason. However, the code does work on another computer. It just seems to be some memory issue that does not is just not fixing or is not improving. But once I do find something, if there is something that I could improve or fix it or find a way to fix it, I definitely will post something about it. But before that, we'll just be going through the last part of the shadow mapping code. We'll be doing PCF with point lights this time, and then we'll be working on a few improvements of the other lights and just cleaning up a few pieces of the code here. Alright, so we will start in object.fs in the calculate point light shadow function, and for our PCF here, in PCF with the spotlights and the directional lights, we were looking at 2D offsets because the texture was just a 2D plane, and that's how we rendered the shadows. However, now that we have a cube map, we have to have 3D offsets, which will increase the number of offsets that we want. And there's actually just a good list of them on learnopengl.com. I will put the link to this in the description. But you can just put this array and just put it into object.fs just as a global variable. And it's just a list of 20 vectors, and the one thing I would recommend is changing the last vector to a 0, 0, 0, so we actually do get the value at the point. So you should have this, and then if you can modify these, this just has to have a good representation of all the possible directions. And then once again, just change the last one to 0, 0, 0. Alright, now in calculate point light shadow, what we're going to do is, like before, we're gonna have our bias, and then instead of still not alright, we're gonna have a sum of the shadows so we can take an average. So we'll have PCF here. So float shadow is equal to 0.0. Then we'll do for int I is equal to 0, I is less than 20. We're just going to have 20 as the number of textures. We can actually create a define here. I'll just say hashtag define number of samples is 20. And then I will just put that, use that macro in the array size there, just so we can standardize it. So I is less than number of samples, I plus plus. And then we're going to get the closest depth here. So float closest depth is equal to texture point lights at idx.depth buffer light to frag plus sample offset directions at I, and then just get the R value from that texture. So this is pretty much the same thing that we did with the spotlights. We're just getting each depth value in the cube map, and then we're gonna multiply it by the far plane as we did with the singular closest depth. Closest depth times equals point lights at idx dot far plane using the uniform variable in the structure, and then if current depth minus bias is greater than closest depth shadow plus equals 1.0. So if the current depth is greater than the closest depth, then it's going to be in the shadow. And then at the end, we will say shadow divided by equals. Then we'll cast the number of samples. This was giving me an error for some reason when I was trying to cast it to a float. So if not, just put a 20.0 here, and it won't make a difference. And then at the end, return shadow. Alright, so I wish I could, I'll try running it again, but we're not going to see anything, I don't think. Which sucks, yeah, and we got an error. Alright, so it doesn't like that we're casting something. So yeah, just make this 20.0 here. And then you won't get any errors, but we still have this shit there. I'll actually create a define here. Define num samples f 20.0, and then we can just use this here. And that should not give us any errors. Perfect. Alright, so that's pretty standard. Now there's actually a bit of a cool thing that we can do with soft shadows. So soft shadows means that the transition between something that's not in the shadow and something that is in the shadow is going to be less defined. So we're doing this with PCF, that's part of it. But then it also, another contributing factor is actually the distance that you are away from a fragment. So the view distance will be, if you're farther away, if the distance is greater, then the shadow will be less defined, so we just want to make it softer. And as a result, we're going to have some factor here called the disk radius that we will multiply the offset by, so it can blend values from a further offset. So we will create a new vector in main here. Let me just make sure I'm doing this right. Yeah, in main. And we're going to call it vec3 view vec is equal to view position minus frag position. And then view direction will now just be the normalization of view vec. So this is just the vector from the fragment to the viewer, and then we just normalize that to get the direction, which is what we had before. Now we have to add this as a parameter to the calc point light function, so I'm just going to have that here before the view direction, so vec3 view vec, put that in there, and then I will copy and paste this parameter, the 3D vector, into both calc point light shadow. I'll do that after norm, and then calc point light, just so the signatures match up. Now in calc point light shadow, we're going to go to where we do the PCF. It's over here. And then underneath where we have the shadow variable, we'll create another float here. Float view distance is equal to the length of the view vector. And then float disk radius is equal to 1.0 plus, and then in parentheses, view distance divided by point lights at idx.farplane. And then divide that whole thing by 30.0, which is just an arbitrary number. The higher you make this number, the more defined it'll be, because the disk radius will be closer to a 1. Or to a 0 for that matter. Because you're just making this value smaller and smaller, but if you make it 1, or close as this factor approaches 1, you see more of the pixel, but 30 is a good balance. And now all we have to do is multiply the sample offset direction by disk radius. So once again, if you are further out from the fragment, if the camera is further out from the fragment, the disk radius will be larger. So this the offset will take a larger, the offset will be further away from the point. And we can do something similar in the, can we do something similar in the spotlights? Let me see. Yes, we can. All right. So in the spotlights and the direction lights, let's also pass in another parameter, view vec. So just copy the comma and then vec3 view vec, and we're going to paste it into every single function actually in here after the normal. So calc spotlight shadow, calc spotlight, and we're going to have to pass it in as a parameter there to the shadow function, calc dirlight and calc dirlight shadow. And before we do anything else, let's go into calc spotlight and actually pass in the view vec as a parameter to calc spotlight point light shadow. And we will have to do this for each of the functions, but make sure your ordering is correct. So I'm just going to do that over here. And then in directional light, it's the same story. All right, so let's start in direction, or let's take the code that we have. So you can just copy the disk radius, and we have a far plane for the spot and point lights, but we do not have it yet for the directional light, so we'll have to pass that in as a uniform variable, which is okay. So let's go into calc Light and go ahead and copy the definition of, or the assignment of, where is it? It's over here, of disk radius, so the float disk radius that we did in calc point light shadow, and we're going to copy it and paste it into the functions here. So in calc light shadow, we say float disk radius is equal to 1.0 plus the view distance, which we actually also need to calculate here. So float view distance is equal to the length of view vec. So we're going to copy these together actually. So you get the length of the view vector, then the disk radius is 1.0 plus the view distance divided by, now instead of the point lights dot far plane, we're going to say dir light dot far plane, and we will configure that as a uniform variable in just a second. And then we'll copy both lines this time, the view distance and disk radius, and we're going to go into calc spotlight shadow. And then we will say now, instead of dirlight.farplane, just do spotlights at idx.farplane. And then in the actual PCF calculation, we're going to say PCF depth is equal to that, and then the vec2xy, which is the offset, times the texel size to convert it to pixels, and then we're going to say times disk radius. Or we should actually do disk radius first, and that, or does it make a difference? It does not make a difference at all, no. Alright. No, it doesn't. It doesn't make a difference. Alright, perfect. And then we also, I forgot to do this, but we need to do the multiplication by the disk radius in calc directional light shadow as well. So once again, when we get the PCF depth, we're going to say the second parameter is projection coordinates dot xy plus the vector 2 of xy, which is the offset, times the texel size, and then times disk radius now. Alright, that's that. And then one thing that, or another thing that we can get rid of is in object dot in the calc light shadow, we don't need this closest depth calculation anymore because we do that in the PCF. And then this is also applies for the calc spotlight shadow, and we can get rid of the float z, or what can we do? We can get rid of the closest depth and z, so where we say get the closest depth in the buffer and also linearizing the depth, because these are unused. And just to make sure, I will run this just to okay, we get, oh yeah, all right, so the directional light does not have the structure. All right, that's fine. All right, so we can configure that right now. In directional light, just add a float for the far plane as we have with the point light. In object.fs, it's just another structure variable. And then we have to configure this now in light.cpp, where we actually render to the shader. So directional light.render. We're going to say shader.setFloat, and then the name will be dirlight.farplane, and then the value will be, what is our directional light? It is br dot max.z. So if you remember, for our directional light, we have kind of a shadow box that we render into, and our maximum z coordinate on that box is the maximum depth, which is essentially acting as our far plane. And you can see that when we calculate the orthographic projection here, where br.max.z is considered as the far plane. Alright, so now if we run this, we should get no... Alright, we're still getting stuff. 122. Yes, alright, so we did not pass in the view vector, so make sure that when we call the calc light, calc point line, calc spotlight, that we're passing in view vec with the other stuff. Forgot to do that. Alright, and then just run this again. Nope, we're still getting stuff. I may have messed up the ordering. It goes norm view dir. Wait, that's... I forgot to add the... Alright, so before you run this, just make sure that the view vector is a parameter in the function signatures for calc dir light, calc point light, and calc spotlight, and then also in the body definitions, because we separated those. So in the first 3 lines up here, the parameters must be present. Then in the bodies down here, they must be present in each of the 6 functions that we use. So the shadow calculation, and then also just the calculation functions. And then when we call each of those functions in main, we need to pass in view vec in its respective position. So now if we run this, god damn it, we're still getting stuff. Incompatible type for parameter number 127. Did I forget to, I probably, oh, yeah. Alright, once again, I forgot to add it as a parameter. It's a simple fix. There we go. Alright, so no shader compilation errors. Once again, I'm sorry that you don't get to see an example of what everything should look like. View vec, and view vec. Perfect. Alright, so that's the first thing. And then the second thing is actually going to be, we made an error when we were doing the shadow, or the shadow calculation for the spotlight. The reason why is because in the PCF, we just take this value as is. So we're considering it, we're assuming it's linear. However, that's not the case, since the spotlight uses a perspective matrix. Now when we actually did a linearization formula on the singular coordinate when we did not use PCF in the spotlight, so that was there. However, to avoid having to linearize each of these PCF depths, we can do something similar to what the point light does, and actually and do a half linearization within the fragment shader itself. So we are going to we'll stay in object.fs for right now, because we're going to follow the procedure that point light does. So in point light, we get the closest depth for each PCF value, for each PCF coordinate, and this just gets the linearized value in 0 to 1, and then we multiply it by the far plane, and that's for each of them. So now I'm actually just going to change this name to PCF depth, just so it's consistent. And then, so now what we'll do in calc spotlight shadow is, for each PCF depth, we're going to say PCF depth times equals spotlights at idx dot far plane. And the reason why, once again, is because when we linearize, we put it into a range of 0 to 1, which are the values that the texture can actually hold. And then we just map it back to 0 to the far plane. Alright, now we're going to need to actually create this linearization in the in the fragment shader for the spotlight shadow. So this is going to create a little bit of rearranging of files in our fragment, just our shader files in general, because we're going to have to create a new one and then also change some names. So let's change our names first. With shadow.vs, we're going to rename it to dir spot shadow.vs. The reason why is because this is being used by the directional light and the spotlight. Now, in order to actually linearize the depth, if we look at point shadow.fs, which provides the example that we will follow, we need a light position, a far plane, and a fragment position. The light position and the far plane are uniform variables, so we can take care of those later, but the fragment position has to be calculated and passed in by another shader, by the vertex shader. So the dir spot shadow.vs has to output a vector for fragment position. So out vec for frag position, and this is going to be stuff that we've seen so far, and we can actually just split up the calculation right here. So in main, we're going to say frag pose is equal to the vector 4 of a size times a pose plus a offset, and then 1.0. So this is exactly what we have here, and then we just need to multiply the light space matrix by frag pose, because these we just put the model translation into the frag pose. So now frag pose passes that in to the fragment shader, which is in which, like I said, is going to be the exact same as the point light fragment shader. So we can rename point shadow.fs to point spot shadow.fs, because it's going to be used by the point light and the spotlight shadow. The point shadow and the vertex and geometry shader remains the same, and then for shadow.fs, since it's only being used by the directional light now, we're going to rename it just to dir shadow.fs, just like that. And remember, that's an empty fragment shader. So once again, in point spot shadow.fs, we're going to linearize the depth to a value that will allow us to simplify the calculations in the object.fs. All right. Now in main.cpp, what we have to do is just take these the new paths and just insert them in the shader. So we're going to have 3 shaders now. I tried to avoid this. I tried to be smart last time, but I completely I just completely ignored the fact that the depths in the spotlight texture were not linearized. So we're gonna have 3 shaders for the shadows now. We're gonna have a dir shadow shader. Then we will have a spot shadow shader, which will take in the paths of assets slash shaders slash shadows slash dir spot shadow.fs or .vs for the vertex shader, and then for the fragment shader, it's going to be assets slash shaders slash shadows slash it's going to be point spot shadow.fs, and then we have to rename the path in point shadow shader. The fragment shader goes from point shadow.fs to point spot shadow.fs. And then for the directional light, the shadow.vs will go to dir spot shadow.vs, and shadow.fs will go to dir shadow.fs. So just make sure that the files correspond to their corresponding shaders here. Now in the main loop, what we're going to have to do is we're going to have to use these new shaders. So when we do the directional light, we're going to say scene.render dir light shader and pass in the dir shadow shader, and then render scene with the dir shadow shader. Point shadow shader remains the same, and then for the spot light shader, we're going to have to use a new one. So in the for loop here, we're going to say scene.render spotlight shader and pass in the spot shadow shader, and then render scene with spot shadow shader. Alright. And then we can also uncomment some of the stuff for the spotlights here. Just gonna Alright, so yeah, these are our 3 new shadows, or our 3 new shaders. Well, not new ones, or 1 new and our 2 renamed ones. And then just the last thing that we have to do is actually set those uniform variables. So in point spot shadow .fs, we need a light position in the far plane, and the simple way to fix this is going to be in scene.cpp, where we actually render the shaders to render the shadow shaders. We just need to go to that function, which is over here, render spotlight shader. And all we're going to do is, just like we do in the point lights, we're going to set the light position and then the far plane. We can actually copy and paste the 2 assignments here from the point light shader function, and then just change the names of the values. So it goes from point lights at IDX to spotlights at IDX for both the position and the far plane. And once again, we're doing this because they're using the same shader now. So let me build, and just make sure there's no errors. Looking good. Let me run this to make sure that there's no error. All right. Must write to dirspot_shadow.vs. What do you mean? I write to GL position. This is weird. Let me try running this. It's not gonna make a difference. Could not open assets. Oh yeah, I mistyped the name. All right. Yeah, make sure your paths are properly spelled. All right. Now if I run this, we don't get any errors, but once again, nothing's happening, which is no bueno. Yeah. So that's just, we're finishing up shadows. I hope I'll figure out why stuff isn't rendering, and if I figure that out, I will definitely post something talking about that. But yeah, that's we're done with shadows. We'll be doing some more lighting stuff. We'll be doing parallax mapping, normal mapping, and stuff like that. That'll be pretty cool. But yeah, that's all I got to say about that. I hope you guys found this informative. Once again, links will be in the description for the copy and paste stuff, and also a good explanation from where I actually plagiarized everything. But don't worry, I am giving credit where credit is due to Joey DeVries at learnopengl.com. Yeah, check out his Twitter. I'm plugging him. I actually think I remember reading on his website that he was nominated for some magazine award, which I find hard to believe. But, you know, he is a saint, so I actually could believe that, but I don't know. Alright, anyway, hope you guys enjoyed this, and I'll see you guys next time with some more lighting stuff. So, until then, enjoy yourselves and stay safe.